Publications: Audio-driven facial animation by joint end-to-end learning of pose and emotion. We present a machine learning technique for driving 3D facial animation by audio input in real time and with low latency. Our deep neural network learns a mapping from input waveforms to the 3D vertex coordinates of a face model, and simultaneously discovers a compact, latent code that disambiguates the variations in facial expression that cannot be explained by the audio alone. During inference, the latent code can be used as an intuitive control for the emotional state of the face puppet. We train our network with 3 to 5 minutes of high-quality animation data obtained using traditional, vision-based performance capture methods. Even though our primary goal is to model the speaking style of a single actor, our model yields reasonable results even when driven with audio from other speakers with different gender, accent, or language, as we demonstrate with a user study. The results are applicable to in-game dialogue, low-cost localization, virtual reality avatars, and telepresence. Authors Tero Karas, Timo Ila, Samueli Lane, Ani Herva, Remedy Entertainment, Jaakko Lehtinen, NVIDIA and Aalto University. Publication date Sunday, July 30, 2017. Published in SIGGRAPH 2017. Research area: Computer Graphics, Artificial Intelligence and Machine Learning. We present a machine learning technique for driving 3D facial animation by audio input in real time and with low latency. Our deep neural network learns a mapping from input waveforms to the 3D vertex coordinates of a face model, and simultaneously discovers a compact, latent code that disambiguates the variations in facial expression that cannot be explained by the audio alone. During inference, the latent code can be used as an intuitive control for the emotional state of the face puppet. We train our network with 3 to 5 minutes of high-quality animation data, obtained using traditional, vision-based performance capture methods. Even though our primary goal is to model the speaking style of a single actor, our model yields reasonable results even when driven with audio from other speakers with different gender, accent, or language, as we demonstrate with a user study. The results are applicable to in-game dialogue, low-cost localization, virtual reality avatars, and telepresence. Our deep neural network for inferring facial animation from speech. The network takes approximately half a second of audio as input, and outputs the 3D vertex positions of a fixed topology mesh that correspond to the center of the audio window. The network also takes a secondary input that describes the emotional state. Emotional states are learned from the training data without any form of pre-labeling. Expressive facial animation is an essential part of modern computer-generated movies and digital games. Currently, vision-based performance capture, i.e., driving the animated face with the observed motion of a human actor, is an integral component of most production pipelines. While the quality obtainable from capture systems is steadily improving, the cost of producing high-quality facial animation remains high. First, computer vision systems require elaborate setups and often also labor-intensive cleanup and other processing steps. A second, less obvious issue is that whenever new shots are recorded, the actors need to be on location, and ideally also retain their appearance. This may be challenging if, for example, another role requires growing a beard. While audio-based performance capture algorithms are unlikely to ever match the quality of vision systems, they offer complementary strengths. Most importantly, the tens of hours of dialogue spoken by in-game characters in many modern games is much too expensive to produce using vision-based systems. Consequently, common practice is to produce only key animations, such as cinematics, using vision systems, and rely on systems based on audio and transcript for producing the bulk of in-game material. Unfortunately, the quality of the animation produced by such systems currently leaves much to be desired. Further, emerging real-time applications in telepresence and virtual reality avatars present additional challenges due to the lack of transcript, wide variability in user voices and physical setups, and stringent latency requirements. Our goal is to generate plausible and expressive 3D facial animation based exclusively on a vocal audio track. For the results to look natural, the animation must account for complex and codependent phenomena including phoneme co-articulation, lexical stress, and interaction between facial muscles and skin tissue. Hence, we focus on the entire face, not just the mouth and lips. We adopt a data-driven approach, where we train a deep neural network in an end-to-end fashion to replicate the relevant effects observed in the training data. At first, the problem may seem intractable because of its inherent ambiguity. The same sounds can be uttered with vastly different facial expressions, and the audio track simply does not contain enough information to distinguish between the different variations. Petrushian, 1998. While modern convolutional neural networks have proven extremely effective in various inference and classification tasks, They tend to regress toward the mean if there are ambiguities. In the training data,
At first, the problem may seem intractable because of its inherent ambiguity. The same sounds can be uttered with vastly different facial expressions, and the audio track simply does not contain enough information to distinguish between the different variations. Petrushyn 1998. While modern convolutional neural networks have proven extremely effective in various inference and classification tasks, they tend to regress toward the mean if there are ambiguities. In the training data, our method produces expressive 3D facial motion from audio in real time and with low latency. To retain maximal independence from the details of the downstream animation system, our method outputs the per-frame positions of the control vertices of a fixed topology facial mesh. Alternative encodings, Lewis et al. 2014, such as blend shapes or nonlinear rigs, can be introduced at later pipeline stages, if needed for compression, rendering, or editability. We train our model with 3 to 5 minutes of high-quality footage obtained using traditional, vision-based performance capture methods. While our goal is to model the speaking style of a single actor, our model yields reasonable results even when driven with audio from other speakers with different gender, accent, or language. We see uses for this technology in in-game dialogue, low-cost localization, virtual reality, and telepresence. It could also prove useful in accommodating small script changes even in cinematics. To related work, we will review prior art and systems whose input is audio or text and output is 2D video or 3D mesh animation. We group the approaches into linguistic and machine learning-based models, and also review methods that support apparent emotional states. Models based on linguistics. A large body of literature exists for analyzing and understanding the structure of language, and translating it to anatomically credible facial animation. Lewis 1991, Mathieses and Verhelst 2015. Typically, an audio track is accompanied with a transcript that helps to provide explicit knowledge about the phoneme content. The animation is then based on the visual counterpart of phonemes called Weissamase, Fisher 1968, through complex rules of coarticulation. A well-known example of such a system is the dominance model, Cohen and Massaro 1993, Massaro et al. 2012. In general, there is a many-to-many mapping between phonemes and Weissamase, as implemented in the dynamic Weissamase model of Taylor et al. 2012, and in the recent work dubbed Jolly, Edwards et al. 2016. Jolly factors the facial animation to lip and jaw movements based on psycholinguistic considerations, and is able to convincingly reproduce a range of speaking styles and apparent emotional states independently of the actual speech content. A core strength of these methods is the explicit control over the entire process, which makes it possible to, e.g., explicitly guarantee that the mouth closes properly when the puppet is spelling out a bilabial per meter, b/p, or that the lower lip touches the upper teeth with labiodentals, f/v. Both are difficult cases even for vision-based capture systems. The weaknesses include the accumulated complexity of the process, language-specific rules, need for a near-perfect transcript for good quality, typically done manually, Edwards et al. 2016, inability to react convincingly to non-phoneme sounds, and lack of a principled way to animate other parts of the face besides the jaw and lips. FaceFX, www.facefx.com, is a widely used commercial package that implements the most widely used linguistic models, including the dominance model, models based on machine learning. Here we will group the systems primarily based on how they use machine learning. Voice puppetry, brand 1999, is driven exclusively using audio and does not perform explicit analysis of the structure of the speech. In the training stage, it estimates a hidden Markov model, HMM, based on the observed dynamics of the face in a video. During inference, the HMM is sampled and the most probable sequence is synthesized through trajectory optimization that considers the entire utterance. Subsequent work has improved the trajectory sampling, Anderson et al. 2013, Wang and Sung 2015, and replaced which does piecewise linear approximation, with alternative representations such as Gaussian process latent variable model. Dina and Galata 2009, Dina et al. 2013, hidden semi-Markov model, Chabas et al. 2014, or recurrent networks, Fan et al. 2016. Alternatively, machine learning has been used for learning coarticulation, Deng et al. 2006, Ezid et al. 2002, followed by a concatenation stage to synthesize animation, or for mapping between various stages, such as phoneme classification, Scherziger and Magnanath-Thalmann 2000, mapping text to phonemes and phonemes to Visamaze, or mapping input audio features to control parameters of a Gaussian mixture model, Hofer and Richmond 2010. Given that our goal is to produce 3D animation based on audio, we are not inherently interested in the intermediate representations. Instead, we would like to formulate the entire mapping as an end-to-end optimization task. The early experiments with neural networks used audio to directly drive the control parameters of an animated 3D mesh, Hong et al. 2002, Massaro et al. 1999, Oman and Salva 1999, but the networks back then were necessarily of trivial complexity. We revisit this end-to-end formulation with deep convolutional networks, latest training methods, and problem-specific contributions. It is unfortunately difficult to do apples-to-apples comparisons against previous systems that use machine learning. The majority of work has focused on reusing captured video frames with concatenation, blending, and warping. Such image-based methods, e.g. Anderson et al. 2013, Dina et al. 2013, Ezid et al. 2002, Fan et al. 2016, Liu and Osterman 2011, Wang and Sung 2015, can produce realistic results, but typically need to store a large corpus of frames, and are not directly applicable to applications such as games or VR that need to animate and render 3D models from free viewpoints. Typically with flexible identities, the systems that do produce 3D are often based on text input instead of audio, Chabas et al. 2014, Wampler et al. 2007. We are not aware of any publicly available implementations of methods that would suit our needs, e.g., Deng et al. 2006, and it would not be fair to compare against the result videos of old methods since the quality standards have risen dramatically. In sync with the available computing power, extracting and controlling the emotional state. The automatic separation of speech and emotional state has been studied by several authors. Chuang et al. 2002, build on the work of Tenenbaum and Freeman 2000, and use a bilinear model for separating the apparent emotional state from speech Visamaze. This was later generalized, in closely related topics to multilinear, Vasilescu and Terzopoulos. 2003, Wampler et al. 2007, and nonlinear models, Elgamal and Li 2004, as well as independent component analysis, Cao et al. 2003, Cao et al. 2005, extract emotions using support vector machines, and synthesize 3D animations based on speech and apparent emotional state. They compute mappings between a set of pre-defined emotional states, and let the user specify the state to be used for animation synthesis. Deng et al. 2006 compute an eigenspace for expressions based on a predefined set of emotional states. Wampler et al. 2007 also allow a user-specified emotional state. Anderson et al. 2013 use cluster adaptive training to derive a basis for the emotional state so that it can be interpolated and extrapolated. They also present a user study rating the level of realism in emotion synthesis. Covering several methods, Cao et al. 2005, Liu and Osterman 2011, Mélenchon et al. 2009, Zhao et al. 2014 use neural networks to learn a mapping from PAD pleasure-displeasure, arousal-non-arousal, and dominance-submissiveness parameters to facial expressions. What distinguishes our method from all these efforts is that instead of having predefined categories for emotions, we let the Network learn a latent, low-dimensional descriptor that allows it to explain the data. The descriptor's parameter combinations can form an analysis network. Residual motion. Almost, but not quite, human-like appearance. And motion is often perceived as particularly creepy, an effect known as the uncanny valley, Mori 1970. Several authors have tried alleviating the effect by deducing additional motion, such as head movements, eye saccades or blinks from audio, e.g., Deng et al. 2004, Marcella et al. 2013. In our work, we assume that such residual motion is driven by higher-level procedural controls, such as a game engine, and limit our scope to motion that is directly related to articulation. 3. End-to-end network architecture. We will now describe the architecture of our network, along with details on audio processing and the separation of emotional state from the speech content. Given a short window of audio, the task of our network is to infer the facial expression at the center of the window. We represent the expression directly as per vertex difference vectors from a neutral pose in a fixed topology face mesh. Once the network is trained, we animate the mesh by sliding a window over a vocal audio track and evaluate the network independently at each time step. Even though the network itself has no memory of past animation frames, it produces temporally stable results in practice. 3.1 Architecture Overview. Our deep neural network consists of one special-purpose layer, 10 convolutional layers, and 2 fully connected layers. We divide it in 3 conceptual parts, illustrated in Figure 1 and Table 1. We start by feeding the input audio window to a formant analysis network to produce a time-varying sequence of speech features that will subsequently drive articulation. The network first extracts raw formant information using fixed-function autocorrelation analysis, section 3.2, and then refines it with 5 convolutional layers. Through training, the convolutional layers learn to extract short-term features that are relevant for facial animation, such as intonation, emphasis, and specific phonemes. Their abstract, time-varying representation as the output of the 5th convolutional layer. Next, we feed the result to an articulation network that consists of 5 further convolutional layers that analyze the temporal evolution of the features and eventually decide on a single abstract feature vector that describes the facial pose at the center of the audio window. As a secondary input, the articulation network accepts a learned description of emotional state to disambiguate between different facial expressions and speaking styles. Section 3.3. The emotional state is represented as an e-dimensional vector that we concatenate directly onto the output of each layer in the articulation network, enabling the subsequent layers to alter their behavior accordingly. Each layer outputs FL times WL times HL activations, where FL is the number of abstract feature maps, WL is dimension of the time axis, and HL is the dimension of the formant axis. We use stritted 1 times 3 convolutions in the formant analysis network to gradually reduce HL while increasing FL, i.e., to push raw formant information to the abstract features, until we have HL equals 1 and FL equals 256 at the end. Similarly, we use 3 times 1 convolutions in the articulation network to decrease WL, i.e., to subsample the time axis by combining information from the temporal neighborhood. We chose the specific parameters listed in Table 1 because we found them to consistently perform well in our datasets while leading to reasonable training times. The results are not hugely sensitive to the exact number of layers or feature maps, but we found it necessary to organize the convolutions in 2 distinct phases to avoid overfitting. Importantly, the formant analysis network performs the same operation at every point along the time axis, so that we can benefit from the same training samples at different time offsets. The articulation network outputs a set of 256 plus E abstract features that together represent the desired facial pose. We feed these features to an output network to produce the final 3D positions of 5022 control vertices in our tracking mesh. The output network is implemented as a pair of fully connected layers that perform a simple linear transformation on the data. The first layer maps the set of input features to the weights of a linear basis, and the second layer calculates the final vertex positions as a weighted sum over the corresponding basis vectors. We initialize the second layer to 150 pre-computed PCA components that together explain approximately 99.9% of the variance seen in the training data. In principle, we could use a fixed basis to effectively train the earlier layers to output the 150 PCA coefficients. However, we have found that allowing the basis vectors themselves to evolve during training yields slightly better results. The main input to our network is the speech audio signal that we convert to 16 kHz mono before feeding it to the network. In our experiments, we normalize the volume of each vocal track to utilize the full -1+1 dynamic range, but we do not employ any other kind of processing such as dynamic range compression, noise reduction, or pre-emphasis filter. The autocorrelation layer in Table 1 converts the input audio window to a compact 2D representation for the subsequent convolutional layers. Our approach is inspired by the source filter model of speech production, Benzagiba et al. 2007, Lewis 1991, where the audio signal is modeled as a combination of a linear filter, vocal tract, and an excitation signal, vocal cords. The resonance frequencies formants of the linear filter are known to carry essential information about the phoneme content of the speech. The excitation signal indicates the pitch, timbre, and other characteristics of the speaker's voice, which we hypothesize to be far less important for facial animation, and thus we focus primarily on the formants to improve the generalization over different speakers. The standard method for performing source filter separation is linear predictive coding, LPC. LPC breaks the signal into several short frames, solves the coefficients of the linear filter for each frame based on the first K autocorrelation coefficients, and performs inverse filtering to extract the excitation signal. The resonance frequencies of the filter are entirely determined by the autocorrelation coefficients, so we choose to skip most of the processing steps and simply use the autocorrelation coefficients directly as our representation of the instantaneous formant information. This makes intuitive sense, since the autocorrelation coefficients essentially represent a compressed version of signal whose frequency content approximately matches the power spectrum of the original signal. The representation is a natural fit for convolutional networks, as the layers can easily learn to estimate the instantaneous power of specific frequency bands.
In practice, we use 520 milliseconds worth of audio as input, i.e., 260 milliseconds of past and future samples with respect to the desired output pose. We chose this value to capture relevant effects like phoneme coarticulation without providing too much data that might lead to overfitting. The input audio window is divided into 64 audio frames with 2x overlap, so that each frame corresponds to 16 milliseconds, 256 samples, and consecutive frames are located 8 milliseconds, 128 samples, apart. For each audio frame, we remove the DC component and apply the standard Hahn window to reduce temporal aliasing effects. Finally, we calculate K equals 32 autocorrelation coefficients to yield a total of 64 times 32 scalars for the input audio window. Although much fewer autocorrelations, e.g. K equals 12, would suffice to identify individual phonemes, we choose to retain more information about the original signal to allow the subsequent layers to also detect variations in pitch. Our approach differs from most of the previous work on speech recognition, where the analysis step is typically based on a specialized techniques such as Mel-frequency cepstral coefficients (MFCC), perceptual linear prediction (PLP), and Rostov filtering (Benzagiba et al. 2007. These techniques have enjoyed wide adoption mainly because they lead to good linear separation of phonemes and consequently work well with hidden Markov models. In our early tests, we tried several different input data representations and observed that the autocorrelation coefficients were clearly superior for our case. 3.3 Representation of emotional states. Inferring facial animation from speech is an inherently ambiguous problem, because the same sound can be produced with very different facial expressions. This is especially true with the eyes and eyebrows, since they have no direct causal relationship with sound production. Such ambiguities are also problematic for deep neural networks, because the training data will inevitably contain cases where nearly identical audio inputs are expected to produce very different output poses. Indeed, Figure 2 shows several examples of conflicting training data where the input audio clip consists entirely of silence. If the network has nothing else to work with besides the audio, it will learn to output the statistical mean of the conflicting outputs. Our approach for resolving these ambiguities is to introduce a secondary input to the network. We associate a small amount of additional, latent data with each training sample, so that the network has enough information to unambiguously infer the correct output pose. Ideally, this additional data should encode all relevant aspects of the animation in the neighborhood of a given training sample that cannot be inferred from the audio itself, including different facial expressions, speaking styles, and co-articulation patterns. Informally, we wish the secondary input to represent the emotional state of the actor. Besides resolving ambiguities in the training data, the secondary input is also highly useful for inference. It allows us to mix and match different emotional states with a given vocal track to provide powerful control over the resulting animation. One way to implement emotional states would be to manually label or categorize the training samples based on the apparent emotion. This approach is not ideal, however, because there is no guarantee that a predefined labeling actually resolves ambiguities in the training data to a sufficient degree. Instead of relying on predefined labels, we adopt a data-driven approach where the network automatically learns a succinct representation of the emotional state as a part of the training process. This allows us to extract meaningful emotional states even from in-character footage, as long as a sufficient range of emotions is present.
We suspect that this is because the emotional state aims to control the animation on multiple abstraction levels, and the higher abstraction levels are generally more difficult to learn. Connecting to the earlier layers provides nuanced control over subtle animation features such as co-articulation, whereas connecting to the later layers provides more direct control over the output poses. It makes intuitive sense that the early stages of training will need to concentrate on the latter, while the later stages can concentrate on the former once the individual poses are reasonably well represented. The learned emotional states are just data without semantic meanings, sad, happy, etc. We defer the discussion about semantics to Section 5.1 because they do not play a role in the network architecture or training. For training, we will now describe the aspects relevant to training our network. How the training targets were obtained, what our dataset consists of, dataset augmentation, loss function, and training setup. 4.1 Training targets. We obtained the 3D vertex positions used as training targets using the commercial DI4D Pro system, www.d4d.com, that employs 9 synchronized video cameras at 30 Hz to directly capture the nuanced interactions of the skull, muscles, fascia and skin of an actor, excluding high-frequency details such as wrinkles. The benefit of this system is that it allows us to bypass complex and expensive facial rigging and tissue simulations for digital doubles. The input and output data is illustrated in Figure 3. As the first step, an unstructured mesh with texture and optical flow data is reconstructed from the 9 images captured for each frame. A fixed topology template mesh, created prior to the capture work using a separate photogrammetry pipeline, is then projected on to the unstructured mesh and associated with the optical flow. The template mesh is tracked across the performance, and any issues are fixed semi-automatically in the DI4D track software by a tracking Artist. The position and orientation of the head are stabilized using a few key vertices of the tracking mesh. Finally, the vertex positions of the mesh are exported for each frame in the shot. These positions, or more precisely the deltas from a neutral pose, are the desired outputs of our network when given a window of audio during training. One limitation of video-based capture setups is that they cannot capture the tongue since it is typically not visible in the images. While the exact control of the tongue is highly relevant for speech production, it is rarely visible so clearly that it would have to be animated in detail. We thus leave the tongue as well as wrinkles, eyes, and residual head-body motion to higher-level procedural animation controls.
4.2 Training Data Set. For each actor, the training set consists of two parts, pangrams and in-character material. In general, the inference quality increases as the training set grows, but a small training set is highly desirable. Due to the cost of capturing high-quality training data, we feel that 3 to 5 minutes per actor represents a practical sweet spot. Pangrams. This set attempts to cover the set of possible facial motions during normal speech for a given target language, in our case English. The actor speaks 1 to 3 pangrams, i.e., sentences that are designed to contain as many different phonemes as possible, in several different emotional tones to provide a good coverage of the range of expression. In character material, this set leverages the fact that an actor's performance of a character is often heavily biased in terms of emotional and expressive range for various dramatic and narrative reasons. In case of a movie or a game production, this material can be composed of the preliminary version of the script. Only the shots that are deemed to support the different aspects of the character are selected so as to ensure that the trained network produces output that stays in character even if the inference is not perfect, or if completely novel or out-of-character voice acting is encountered. For Character 1, our training set consists of 9,034 frames, 5 minutes. 1s, of which 3,872 come from pangrams and 5,162 from in-character material. Additionally, 1,734 frames are reserved for validation. For Character 2, our training set consists of 6,762 frames, 3 minutes. 45s, of which 1,722 come from pangrams and 5,040 from in-character material. Additionally, we have 887 frames for validation. 4.3 Loss function. Given the ambiguous nature of our training data, we must take special care to define a meaningful loss function that we wish to optimize. We use a specialized loss function that consists of 3 distinct terms, a position term to ensure that the overall location of each output vertex is roughly correct, a motion term to ensure that the vertices exhibit the right kind of movement under animation, and a regularization term to discourage the emotion database from containing short-term variation. Simultaneous optimization of multiple loss terms tends to be difficult in practice, because the terms can have wildly different magnitudes and their balance may change in unpredictable ways. During training, the typical solution is to associate a predefined weight with each term to ensure that none of them gets neglected by the optimization. However, choosing optimal values for the weights can be a tedious process of trial and error, and it typically needs to be repeated whenever the training set changes. To overcome these issues, we introduce a normalization scheme that automatically balances the loss terms with respect to their relative importance. As a result, we automatically put an equal amount of effort into optimizing each term, and there is consequently no need to specify any additional weights. Position term. Our primary error metric is the mean of squared differences between the desired output Y and the output produced by the network Y. For a given training sample X, we express here, V represents the total number of output vertices and Y I denotes the ith scalar component of Y equals Y 1, Y 2, Y 3 V. Closing parenthesis dot. The total number of output components is 3 volts, because our network outputs the full 3D position for each vertex. Motion term. Even though the position term ensures that the output of our network is roughly correct at any given instant in time, it is not sufficient to produce high-quality animation. We have found that training the network with the position term alone leads to a considerable amount of temporal instability, and the response to individual phonemes is generally weak. This motivates us to optimize our network in terms of vertex motion as well. A given Output vertex should only move if it also moves in the training data. And it should only move at the right time. We thus need a way to measure vertex motion as a part of our loss function, similar to Brand's work on HMMs 1999, where both position and velocity are optimized. The standard approach for training neural networks is to iterate over the training data in mini-batches, where each mini-batch consists of B randomly selected training samples x1, x2, xb. To account for vertex motion, we draw the samples as B2 temporal pairs, each consisting of 2 adjacent frames. We define operator M as the finite difference between the paired frames. We can now define the motion term mx.
Inference and results. Once trained, the network can be evaluated at arbitrary points in time by selecting the appropriate audio window, leading to facial animation at the desired frame rate. On our Theno implementation, inference takes 6.3 milliseconds for a single frame and 0.2 milliseconds frame when a batch of 100 frames is processed at once. Given that Theno is known for its large overheads, we are confident that it would be possible to push the single frame performance, which matters for real-time use, below 1 millisecond by using a more efficient framework, e.g., CUDNN directly. The latency of our method is determined by the audio window size, which currently reaches 260 milliseconds to the future. Co-articulation sets a lower bound for the look ahead. We have confirmed experimentally that we can limit the look ahead to 100 milliseconds during training, with minor degradation in quality, even though some co-articulation effects are known to be longer. Schwartz and Savario 2014. Shortening the look ahead further than this leads to a quick drop in perceived responsiveness, so realistic lower bound for the latency of our method therefore seems to be around 100 milliseconds. Methods relying on explicit trajectory optimization, e.g., Brand 1999, Dina et al. 2013, Fan et al. 2016, have substantially higher latency. 5.1 Emotional states. When inferring the facial pose for novel audio, we need to supply the network with an emotional state vector as a secondary input. As part of training, the network has learned a latent e-dimensional vector for each training sample, and our strategy is to mine this emotion database for robust emotion vectors that can be used during inference. During training, the network attempts to separate out the latent information, i.e., everything that is not inferable from the audio alone, into the emotion database. However, this decomposition is not perfect and some amount of crosstalk remains between articulation and the overall expression. In practice, many of the learned emotion vectors are only applicable in the neighborhood of their corresponding training frames and are not necessarily useful for general inference. This is to be expected, because our training data will necessarily be too limited to cover all phonemes and coarticulation effects for every observed emotional state. Accompanying video. Since it is impossible to demonstrate the quality of our animation results using text and images, we refer the reader to the accompanying video. The video includes comparisons with video-based performance capture and dominance model, as well as a final render from a game engine. We also compare our results against dynamic Bisomaze and Jolly using the original video and audio footage from Taylor et al. 2012 and Edwards et al. 2016. Note that in these comparisons we drive our network using a speaker different from the training set. We observe that our results are fluent, expressive, and have good temporal stability in the entire face region. Because our method generalizes well over different speakers, it can also be used with synthetic audio. As an experiment, we ran our method with audio that was synthesized using WaveNet. Van den Ord et al. 2016, a deep neural network that generates audio based on input text. As shown in the video, our method produces natural-looking animation from both male and female synthetic voices. To further probe the limits our method, we ran it for the speakers and languages featured in Table 3 with several different emotional states. As shown in the video, the English-trained network responds surprisingly well in most cases, but it can have trouble keeping up if the input audio has very different tempo compared to the training data.
Our primary focus is on generating high-quality facial animation for in-game dialogue, and we plan to continue evaluating the practical value of our method in a production setting. We have also performed several informal experiments to gauge the suitability of our method. For more general-purpose use, using audio clips recorded in a casual setting with consumer-grade equipment and varying levels of background noise. In general, our method appears to remain responsive, as long as the input volume level is normalized to roughly match the training data, and the animation looks plausible as long as it is displayed in sync with the audio and the tempo of the speech is not too fast. In the future, we hope to see a more principled study of these and related effects in a realistic interactive setting with two or more speakers. We feel that the main shortcoming of our method is the lack of fine detail present in the performance capture data. Combining our approach with generative neural networks might enable better synthesis of such detail and possibly also residual motion for, e.g., the eyes. While our method is able to produce plausible results for several different emotional states based on just 5 minutes of training data, increasing the size of the dataset would likely improve the results even further. It would be particularly interesting to train the network simultaneously for several different characters in attempt to learn a latent, unified representation of character identity. Conceivably, one could also deduce the emotional state automatically during inference based on a longer-term audio context. Acknowledgements. We wish to thank Julian Kostov and Derek Hagen for acting, and Marcus Holtmans for German voice acting, Pauli Kempinen for the ambient occlusion renderings, our colleagues at NVIDIA Helsinki for participating in the user studies, and the deep learning team for compute resources, Jolly authors for comparison videos, and helpful suggestions on evaluation, Dynamic Visamaze authors for comparison videos, and WaveNet authors and LibriVox for audio clips, David Lubke for helpful comments and Lance Williams for pointers to related work.